This little reptile may look like a normal little lizard, but it's in fact a creature capable of something that some would define as a miracle. In the blink of an eye, it takes off and dashes away, sprinting on top of the water. Meet the Basilisk Lizard, the water-walking dragon that seems to defy gravity and challenge a lot of what we know about movement and locomotion. Unlike its mythical counterpart, basilisk lizards aren't in the business of causing death with a single glance. In fact, real-life basilisks are not very formidable, and are quite vulnerable to death at the hands of other forest dwellers such as large birds, snakes, and fish. They generally lay motionless, and their cryptic coloration allows them to blend in with the brown hues of branches or dead leaves on the forest floor, or the deep greens of foliage higher up in the trees. When threatened, however, basilisks employ one of the most creative escape strategies known in the animal kingdom. When jolted from their statue-like state, a basilisk lizard's hind limbs whir into action, bicycling across the surface of the water and propelling the tiny lizard up to 15 feet, covering more than 10 times its own body length in a single second. Once this aquatic roadrunner has sprinted as far as it can, it sinks down into the water, far from whatever threat caused it to move in the first place. This seemingly miraculous escape tactic has earned the basilisk the nickname the Jesus Christ lizard in its homeland of Central and South America, and has captured the attention of not only reptile enthusiasts, but of biomechanical engineers looking to recreate this water-walking ability using adaptive robotics. What is it about these seemingly physics-defying lizards that allow them to possess such a biblical ability? And what might these skittish creatures teach us about being able to walk on water ourselves? Basilisk lizards belong to the cascade lizard family, in reference to the round crests atop their heads. This might have earned them their scientific name, Basilicus, which translates to Little King. These little helmeted kings belong to a much grander lineage of superpowered lizards, the iguanians. This suborder includes some 2,000 lizards, from the fearsome, frilled, and spiky lizards in Australia, to the flying acrobats of Southeast Asia gliding across canopies, to a colorful array of hue-shifting chameleons across different continents. But only the basilisk lizard can walk on water, a unique and extreme adaptation that may have come from an ancient ancestor. The Baby basilicus, a 48-million-year-old lizard skull fossil, is a close relative of the basilisk lizard. While there isn't exactly a way to prove that this ancient relative was also able to walk on water, researchers do know that this ancestral species lived during a time where it would have been very useful to do so. The environment was full of the early ancestors of carnivorous mammals, raptors, and even crocodiles, and you can be sure that being able to run on water would have definitely improved chances of survival amidst these predators. So it's entirely possible that the incredible ability to walk on water has been around for an extremely long time. And this survival strategy is still necessary in the modern world, with snakes, predatory birds, and big mammals who would happily snack on a little lizard. They do their best to camouflage, but even the best camouflage can sometimes be discovered by the keen eyes of larger birds, the supercharged smell of snakes, and the prowling of mammals that can even see in the dark of the night. And that's when running on water comes in handy. To fully appreciate the miracle of the basilisk lizard being able to walk on water, consider how most legged animals walk on land. To describe the gait of terrestrial organisms, biokinematic researchers typically refer to the classic spring mass model. Imagine what it's like when you take a step to walk. After you plant your foot firmly into the ground, notice how your leg flexes ever so slightly before you push off, raise your leg, and prepare to take that next step. This slight flexion can be compared to compressing a spring, priming it for expansion as you bounce off your one leg to propel yourself forward. This bouncing gait is common in many forms of terrestrial locomotion, from the galloping of horses to the hopping of rabbits, and it's a particularly efficient way of moving on land. For the basilisk lizard sprinting across a pond, it's easy to see that this model wouldn't be a good fit. For such a spring system to work, the ground you're walking on needs to provide enough resistance for the spring to push against and be primed. But water is, well, water. Unlike solid ground, it's weak, yielding, and gives to most any kind of pressure that's applied to it. Most limbs that attempt to take a step in the water sink, and those that don't, as is the case for the other water walkers of the animal kingdom, typically have to rely on other mechanisms to stay afloat. The water strider, for example, floats atop the surface with the help of its multiple, extremely long, widespread legs with waterproof hairs. The buoyancy created by these legs can support up to 15 times the insect's weight, a useful adaptation for when it's raining and water drops add considerably to their body weight. Waterfowl like ducks and geese can also occasionally be seen to be running on the water, but are usually assisted by flight that allows them to just barely skim the water's surface. The basilisk lizard doesn't have any long, buoyant limbs, and unlike some gliding lizards, the basilisk isn't able to glide or fly. So how does this reptile manage such an incredible task? Using high-speed cameras, researchers have discovered just how the basilisk lizard does it. Instead of the classical bouncing spring model, basilisk lizard hind limbs move in a more bicycling, piston-like fashion, a totally unique form of movement. The piston-like movement of the basilisk can be sequenced into 3 distinct phases, known as the slap, the stroke, and the recovery phase. As the name of the first phase suggests, the basilisk lizard first slaps the surface of the water, which creates a pocket of air that keeps the lizard from sinking. It's this same kind of air cavity forming phase that allows us to skip tiny pebbles across the surface of a lake. In the stroke phase, the lizard starts to propel itself forward, its leg very quickly digging into the air pocket and kicking back as it pushes off the cavity formed in the slap phase. Then, just before the air pocket collapses and water rushes in to sink the basilisk's leg, the basilisk curls its toes and swiftly pulls its leg out of the air pocket before it breaks, transitioning into the next slap-stroke recovery cycle on the other leg. In this sense, basilisk lizards aren't so much water walkers as they are airbenders, forcing bubbles of air beneath their feet at each step they take. With movements so quick on a surface so fragile, the basilisk also employs some tactics to maintain its center of gravity. On the slap phase, the lizard's leg is slightly pushing off towards the midline, while on the stroke phase, the lizard's leg shifts slightly laterally as it tries to right itself. This kind of wobbly, transverse movement, coupled with its flailing upper limbs and a long, rudder-like tail, helps the basilisk to stay balanced as it dashes across the water and gives it its characteristic goofy, almost clumsy-looking way of running. But is this something that all basilisk lizards can do, from the tiniest ones to the absolutely huge ones? Is there a point at which its size prevents it from running on water? A group of researchers found that smaller, juvenile lizards were much more successful at running on water than larger adults, so size clearly plays some role. When they analyzed the gait mechanics required for lizards weighing between 2 grams and 200 grams, they found something interesting. All of them generate more than enough force to stay on the surface of the water, but how they move changes. Small lizards can be pretty sloppy with how they move, because at 2 grams, they can generate 225% of the force needed to maintain their center of mass at a constant position. In fact, the researchers say that a 2-gram lizard could carry another lizard of the same size on its back and still easily run across the water. Lizards that weigh 200 grams, on the other hand, only produce just over the amount of force needed to support their body weight. They have to avoid drag and yank their feet out of the water as quickly as possible, because they're much more likely to sink. No chance of them carrying a hitchhiker on their backs. And this brings us to the next question. Could humans ever do this? If we wore the world's biggest flippers and never skipped leg day at the gym, could we generate the force necessary to walk on water? Unfortunately, not on this planet. Researchers calculated that humans would have to run at 30 meters per second or 67 miles per hour on 1 square meter fins to generate the necessary force. Not even Usain Bolt could manage it. But if we reduce the gravity to only 20% of Earth's gravity, basically getting it to the moon's gravity, we'd have a chance. You'd still have to wear small fins and weigh no more than 73 kilograms, but then it would actually be possible to walk on water. But considering there's no water on the moon, this isn't the most useful information, but who knows what future humans might get up to. Until then, we're more likely to use the Basilisk Lizard for inspiration with our machines. This simultaneously funny-looking and incredible adaptive strategy of the Basilisk Lizard has captivated the attention of researchers in the field of biomimetic robotics. That is, scientists and engineers who take inspiration from movements in nature and emulate it with machinery. In the context of the Basilisk Lizard, that means amphibious robots, which are designed to navigate between terrestrial and aquatic environments. While there are already a number of species of amphibious robots coming in all shapes and sizes, many of these rely on wheeled or leg mechanisms that sink into the water, while others, inspired by the water strider, rely more on buoyancy and thus move across the water considerably slower. While useful, these robotic designs don't quite fill in the niche of function that a water-running robot could provide. A fast and highly reliable robot that could transition almost instantly from land to water and back could be incredibly useful for unmanned rescue missions, research into dangerous terrain, more efficient ocean explorations, and maybe eventually the exploration of alien environments. Consider some of the prototype robots inspired by the water-walking basilisk. This blade-type crawler, developed by Yamada and Nakamura, has blade-like legs attached to a conveyor belt-like mechanism around the robot's body. Compared to other approaches to rough terrain, this mechanism allows for a good balance between the high velocity that a wheeled vehicle provides and the adaptability that a legged robot could provide. And unlike its reptile counterpart, this blade crawler wasn't designed for running away. This tiny robot headed straight towards danger as it was field-tested to explore volcanic areas of Mount Mihara in Japan. The basilisk-inspired robot didn't disappoint, as it waded seamlessly through small ponds and puddles and demonstrated the potential for unmanned observation of otherwise dangerous sites such as active eruptions. Other projects take the inspiration from nature to the extremes, like this lizard spider octopus jellyfish rolling robot. You heard that right. This robot is envisioned not only to be able to walk on water like the basilisk lizard, but also roll and fold up on top of the water like the golden wheel spider and propel itself underwater just as we see octopus and jellyfish do. And if this wasn't impressive enough, researchers also hope to have this robot release a swarm of other baby robots, also engineered to mimic some of nature's best water travelers. While this mind-boggling robot was initially designed for the purpose of deep-sea research and ocean object identification, the authors mention that such an alien-looking robot may potentially be suited for out-of-this-world explorations in unpredictable environments beyond Earth. The Basilisk Lizard is a prime example of how seemingly small scientific curiosities can be transformed into real-world practical applications that have the potential to save lives and provide us with a better understanding of worlds we've never even been to before. Our growing understanding of the basilisk's funky movements has allowed a more analytical approach to recreating this biblical ability, with researchers experimenting with dynamic folding feet and different kinds of rigid and active tails to slowly, hopefully, reach a point where walking on water will be nothing out of the ordinary. But as researchers are starting to realize, manually programming robots to deal with tons of different situations, such as highly variable terrain, from ice to gravel to water to rocks, is time-consuming and also just doesn't work that well. To really unlock the true potential of robots like the Basilisk bot, researchers are starting to use neural networks that allow the robot to learn on its own how to deal with obstacles it faces. This is, without a doubt, the next huge leap in robotics.
Thanks for watching, and if you want more information about wildlife, then don't forget to subscribe and press that bell icon.